Yeah, that was. This and also use R packages to analyze the German credit data. Risk analysis. You can actually look at in Train CRAN. Look at the documentation sections on the left. Click on contributed. Okay. And look at other R documentation again. I think you have seen this page. And under books. Not books, sorry. Under other R documentation. No, I think it's directly under contributed. So on documentation, click on the contributed, and scroll down somewhere. You see this. This guide to credit scoring in R. Basically, this is an analysis of that German credit data. Use different types of models. Mundane and random forest tree model. So you can go look at it, and then I'm still working on grading on that, so not done yet. So I point to you this this PDF guide about that guide to credit scoring. In fact, Red Hat has a function called list rules, list.rules.rpath. If you have recursive partition modeling, you feed that into that list of rules. It's come out with a printing of the rules of how new object was assigned. Okay. Actually that's a prediction rule. But in fact, we do have predict functions in that. I put it online. This is node 10b.r. I should edit. Someone asking about how you predict the values. In this recursive partitioning tree modeling. Here I take this the same example we seen before. This RP2 would be this recursive partitioning of species on petal width and petal length. Suppose I want to look at this too and develop out this model. And for the iris data, method is classification. And we have this result. I think we have run this. We've seen this before, so let me just run up to this. So here, this is three models that we try to model the species against only two variables, petal width and petal length. So we have this, and let's say you want to calculate the apparent error rate of this. Let me first save this the actual class membership of all the friends. I call this actual. So, and to classify the result, okay, basically use a predict. So for every model in R, there's supposed to produce. There's always a predict function, okay, like this. Actually, the function working behind the scene is not predict. It's called predict.rpath. Or you can just call it rpath because this is the method. Okay. Predict will dispatch this to predict.rpath method. So anyway, next time you are kind of wondering what happened, first you can take a look of this package to see what's in there. This is a recursive partition, right? Oops. It's two. So this is number 2. In many packages, you should see that like predict.rpath listed, but not in this case. So you can try, but there's always one like that, although it's not seen like this. Just type predict.rpath. Okay. And not found because it's kept private. You didn't see it from the list. That's why. Okay. You can always get it get a definition. So with that 3 columns that you can extract this. This is when you're really interested in the function definition of this, and maybe you hope that you can tweak these functions into like changing that. But usually we do not care about this, right? We care more about how to use it. Okay, so it's likely you have this help documentation, but you just use help, or maybe regular you can do this, right? So next time, if you ever wonder whether there's a predict function, and usually there is. For the model, you also have this predict function. Okay? And here, this is a model name. In this case, with recursive partitioning. So next time you want to see a help documentation, just type that. Okay? Usually it's there. Okay? So you can see the definition of this, the prediction of that. The types used by default is by default vector means that you just give the class frequencies. Remember in the class notes and look at our basically give this frequency 5000 for Setosa, Versicolor, and Virginica. If observation belong to that, okay. And so Versicolor with this class identity. So these are for vectors. Okay? You look at that, that's a default. Okay. Of course, our interest in the classified result. So we try to predict the class result. Right? So basically, what we're going to use is this type class. Okay? I think you can just use the first character of that. I wonder there may be just automatic type, like a completion matching. Let's see. That's right here. They have this function called this type match dot argument. So it just specifies enough characters to uniquely identify different methods. Okay, so actually it's done by this. I actually tell you that where you can request the classified membership of your observation based on the model. Object will be this prediction model, right? And then the probability, this would be the class probability. I put a posterior probability, so the class probabilities of these different classified nodes. These are terminal nodes. Okay. A matrix contains everything. Okay. So matrix is combination of the 3. Okay. Well, actually, we can see that I have an example later. Anyway, so here this is basic use of this predict.r part. Okay. So let's look at where's class now. So here, this we do classified here. Okay. So it's a classified predict, taking our recursive partition model, and then say type equal plus, or type equal quote C, unquote. You can just use C. Enough characters to specify. Okay. Let's just do this. Of course, then you can tabulate this to get a confusion matrix, right? Okay. This will be confusion matrix of this classification. So we have 6 out of 150. Here, these are we taking all the data. Okay. And then you can specify the IDs, the print numbers, the misidentified prints. Okay, those are misidentified prints. Okay. So if you run this, you can see these are the prints that misclassified. So we can see there's a misclassified Versicolor, so this one. The reds are the misclassified Virginica, right? Okay. So anyway, you have these misclassified identities, and you can actually combine this actual membership, classified membership, class posterior probabilities of the misidentified prints by doing this. Of course, let me run this. So if I put this all together, okay, I only look at the misidentified individual. Okay. So here, these are actual membership of this misclassified prints. Okay. And here, these are the classified membership. So you know there's a mismatch, right? Okay. These are misclassified identities. Okay. And then later have this predict type equal probabilities, right? So all the cross probabilities of this one, we have 0 and 0.02, something like that. That's why this is classified as Virginica, right? So that, the highest probability is 0.978 for Virginica. So that's why we classify as 3, and the rest here this is classified as 2. Okay? So that's the result. Actually, the same result or similar result can be obtained directly through this the predict using metrics. So here, the next command, let me just type this in. Except that output doesn't explain what we have there. Okay. So here we use our recursive partition tree models. Okay, we request type metrics. I mentioned this is combinations of previous, right? Including the vector. Where is this vector? Right here. This is a vector. This is vector part. Okay. This is the frequencies for that class. Okay, 0, 1, 45, and that's why we classify as a Virginica for this one. And here this class frequency is 0, 49, 5. So that's why this one is classified as Versicolor. Okay. So here these are the frequencies, and then here this is classified membership. Okay. And what else do we have? So here these are the class probabilities. Okay. So very similar to the one. Actually, probably just need this one. You don't have to have everything. But here the one I assembled, show you the actual membership, classified membership, and class probabilities. Okay. For that particular. For this terminal nodes that this observation code. Okay. Okay, so here this is the use of predict. Let's try assuming that we have not the complete data, but we have separated the data into trend set and test set. So how do you do this prediction? How do you do this test error? Suppose I do a 60%, 40% split on the data. So 60% on trend set, okay, and 40% on what's the other test set. Okay. Well, it just happened. Well, of course, this probably doesn't work for other problems. In our problems, we know that each from our data set, each species has 50 observations. Anyway, so with this percentage, we get the trend class size. So with this, the class size in the trend data set, we actually obtain this identities of that of this data set. Okay. Probably this won't matter, but this will make the computation below valid. Okay, before we actually do that, so always try to make sure that this is what we intended. Okay. So here I do sorting here. Okay, so basically sorting that make sure the first. If we do sorting, the first 30 would be for Setosa, right? The IDs for the first 30 plants that appears in the trend set. Okay, and then the next 30 would be for Versicolor. Next 30, the last 30 would be for Virginica. Do sorting to be better. Okay. So now we do this R part. Okay. So basically, well, I don't even have to form a separate data frame for this trend set. All I have to do is just call the same function, so with the same model, but we do this subset here because see, a lot of these standard or some extensive package having this modeling method, they always have this common argument called subset, where we can actually subset data set. So in this case, we provide with the IDs, okay, for the trend set. So just use a subset. It would model this correctly, and we have method which is class, right? Classification. Okay. So we have this result, and now we can look at in the trend set the paired error rate like this, right? This is a paired error. Well, confusion matrix. This is confusion matrix in a transect. This is 5 out of how many? 60% of 100. So 90, right? 5 out of 90. So here, this is a trend. This is trending arrow. You look at this result. Let's plot this result and see what turns out here. Okay. This is the tree model for this in this transect. I guess overall speaking, we still have no trouble in Setosa, right? And this two measurements would be enough to separate Setosa from the other two planes. Right? I will still see some misidentified identities with one. There's one misclassified identities here, and then here 4 of them. Okay. You see that? Okay, that's how we get the result. Okay. And now suppose you form the test data set. Okay, this is test data set by here. So this command just remove from the original data, from the full data set, remove those in a transect, so result will be the test set, right? Okay. This will be the test set. And then you run this confusion matrix. Okay. Confusion matrix, the actual membership is taken from this test set of the species, right? A species of the test set. And then classified with predicting RP3, this is the model we just have there, okay? RP3 and iris test of say -5, meaning that except for the last column is our target variables. Okay? So predicting out of the information, actually because of that model, it will pick only 2 columns, right? The model is based on the petal length and petal width. So we only pick those 2 columns. Okay? Although we supply with 4 columns, doesn't matter. Okay? And type is still a classification. And then we have this into confusion matrix. And you can run the test error rate now. You can see that the result. Okay. The confusion matrix is like this. There are 2 misclassified identities on the test set. The test error about 3%, 3.3%. Not too bad, huh? Okay. It's according to this model. Okay. We apply this in the transit. You run this could be different because I didn't. Well, maybe I should have recorded. I probably should start with some random seed. If you use common random seed, you expect the same result. And here I didn't put it down. Okay. So if you have this command, you run it next time, you probably won't get exactly like this. Okay. So because the way we sample, I didn't record the current seed. So it's too late. Okay. Anyway, now let's look at another example where we have this forensic glass example. And remember, you can do this, use a file, not this one. Okay. You can do this file, load the workspace of loading that forensic glass. And actually that code on this command, so you can just do it directly. So, okay. So you can load the data set, forensic glass data set into current folder. I think this is the example we have seen in this class note 10 dollars. So I think I kind of bring that in here, and then we look at predictions as well. Okay? And we look at the Quincy this complexity parameters before. Okay? There's one thing about this output. Actually, I didn't go through the detail. Okay? This is not just one point. So basically, it's a range of values in this complexity parameters. And first number, basically, this is telling you between 1 and between 0.1956 and so on, 0.1956 to 1. And the second one is between 0.0797 to 0.1956. I forgot which way it's a right inclusion, left inclusion, but anyway, this is sort of range of variable, and then this respective cross validation errors and so on. And we look at plot CP. Last time we see something like this, right? See this kind of figures before, didn't we? This is complexity parameter, and on the top axis, this will be the size of the tree. And last time we said it's probably more likely is somewhere around this one, right? Okay. Be enough, this will go below 1 standard error. Okay. And we'll use 1 standard error rule. So more likely it's between this value. So we can cut off. So kind of cut off between. If you look at this one, look at the cutoff between 0.007 to 0.03. So we use a cutoff 0.01 here. So, okay. Anyway, and we can run the tree by using CP equal 0.01. This is one I have shown last time, and this is very hard to tell. Okay. Why we actually use this style? I actually use different style. Okay. But here we have 1, 2. How many terminal nodes we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So yeah, 9 terminal nodes. Okay. Actually, you can try this out if you use a 0.05, CP 0.05. It only has 6 terminals node left, but only identify 5 classes. Okay. But according to original data, there are 6 classes. So there is one particular class completely misidentified. Actually, that's the one that having the smallest number of observations in there. So this is a drawback of that. With very few information, few information, sometimes very hard to classify. So let's say suppose we stay with this model, okay? And you can do classification. Look at class result, okay? So here we have this confusion matrix. Actually, the one class that is completely misclassified has not the least number of observations. The one that we have least number of observations. There are 12 observations on 13 observations. Here we have 17. This is one that will be misidentified. Use only few splits on the result. Okay? So predict is a function to use. When I say that too few splits probably end up with not a good model, is this one. Let me change that. This is not a good model. You change that instead of CP at 0.01, you split at the 0.5. And remember, you look at that CP plot. This is about 1 standard error, so this is probably not this good. You can try this out and then run the last one. Ended up with this kind of model. And you can see what happened here. Here, this is win F, win NF, win NF repeated, right? Okay. And then here, this is con, TABL, head. There's one particular class missing in this terminal node, namely the vehicle, VH. So the VH is completely misidentified, as you can see in the result here. Okay. This row. Right? So definitely that's not a good model. Okay. See a vehicle type of class is completely misclassified. That's right for that. Okay. So definitely not a good model. Actually, we've seen that plot CP already. This with the 6 terminal nodes only, we have the result. Okay, the error is above 1 standard error rule, so it's not a good result. Okay, and try other models. So anyway, yeah, we mean this should be 0.1. Okay. Okay, so use a predict function. Okay, use a predict function to predict the result, and you have choice having like class, type equal class, or type equal, for example, probability. You want to look at class probability, and class equal vector, which is not so useful. Okay, the information not so useful. We can see that from the graphics anyway. Okay. And class type equal matrix. That And last time we also talked about, you can see that the first 3 models that put in this class note, I have modified it so you can download this again. The first 3 models actually, they do not reach the optimum result because the Hessian matrix is not positive definite. Okay? So let's look at this one. I think we run everything anyway. So look at the first neural network model. And I explained this already, right? Isn't it? Okay. This is 4-2-3 network with two neurons or 2 nodes in the hidden layers. Okay. And it's because this is 3-class problem, so the output layer has 3 neurons, right? 1 for each class. Here, these are the weights to that, okay, assigned to each one of these class. So here, this is the bias that's a constant to fit into the hidden layer 1 or hidden layer neuron 1. Okay, and then here, this is input 1 to H1, and then we should have 4 inputs, right? 4 inputs from these 4 variables. Okay, the sepal length, sepal width, and petal length, petal width. So here, there are 4 of them. Okay. So we have from I1 to I4. Where is I4? Right here, right? And then we have B, that's bias or constant term, right? Fit into the hidden layers. Okay. And there's also constant term to output layers as well. Okay, so carry that weight. And if you let's say suppose you accept this one. This is the confusion matrix by this. Looks like this is kind of too good to be true. There's only one misclassified identity. The model is very complicated because it's a black box. So there's no interpretations about this. Or you can say it's all interpreted result. Okay, too many parameters. And the Hessian matrix is not positive definite. So this is not even reach the, or also this is not really the optimum. So according to this model, this complicated model. You see a lot of negative eigenvalues. If Hessian matrix is positive definite, then you should have all positive eigenvalues, but not in this case. I guess to understand this is, we understand in the univariate function, in order to minimize your objective function, you require the, what's that? You require what? The second derivative to be positive, right? So then your functions equate at the first derivative equate to 0 supposed to be the solution for minimization. Okay. So positive, and then you put this in the perspective of say multivariate result, not just univariate. Then you have Hessian matrix. So Hessian matrix is supposed to be positive anyway. The keyword is positive. Okay. But positive in the multivariate sense is actually looking at the eigenvalues. Okay. So here all the eigenvalues are positive. You have the negative and positive mean that you have saddle points. You kind of having this. The solution you got is a saddle point situation. Okay. In some direction you have you can't reach a minimum. In other direction you actually get maximum. Right. It's a saddle point. So we require that, and you can run other thing here. The first one we use linear transfer function. The first few examples just to show like different options you can have. Okay. The first neural network fit we require linear out. Okay. This is linear transfer function. Okay. To request that. Without requesting this, the default is the logistic transfer function. Okay. So here the second fit will be logistic transfer function. Again, the result is not positive definite. Okay? You run this second part, you can see that you still have the mixed signs in the eigenvalues. It's not positive, not optimized yet, but still you see this. Okay? Well, this is not optimized according to this objective function. Okay? I still see only one misidentified identity. Okay? And look at the third model. Here we still set linear out, but with a subset. Okay, here this is subset analysis. Okay, I use a complete randomization. This is probably not a good idea. And in addition to that, the training data set is too small. Right? It's 30 out of 100. See the result. Kind of very. So third model. Okay, on the train set, with 30 observations only. This is not good. Okay? Now let's look at. I probably want to change to different. That's it. Okay. Here is it. Well, this is still 30%, right? The previous example is completely randomized, so you could have unbalanced class representation, right? So representative, so probably it's not a good idea. So just take 15 on each one. This is still 30%. This is still 30% sampling. Okay? But we have the balanced result in the train set. Let me run everything and go through this. Here we have our ID trainer. We have 30% sampling. Okay, we sample in a balanced way, right? We sample 30% of Setosa, 30% of versicolor, and 30% of Virginica. Okay, so that composes our train set. Of course, as I mentioned before, you don't have to do this way. Okay, you don't even have to form this train data set. You can use a subset and fit in the model. Okay? If you like to do that. And here, suppose we come out with a train set. Okay, by selecting these IDs. Okay. And then we scale all the variables here. Okay? So here, this is standardization, right? Okay. Subtract the mean divided by standard deviation. We do this scaling, and then we fit the model with this train set, okay? With the two neurons in the middle, the hidden layer. Now remember, well, actually, according to the documentation, if you add a decay here, this is the kind of change the model a little bit that make it more efficient. Okay, add some decay factor there, and allows the initial weight. Right? When you fit this, you usually come up with a set of initial weights, right? And initial weights are uniformly sampled from -0.1 to +0.1. So this ING is used to set space by that. Okay? So actually, what I say here. So ran equal 0.1, just set initial weights to be randomly picked from between uniform -0.1 to +0.1. So with training, and then here there are 19 weights. It's still quite complicated model. Okay. Now here this is a summary result. Okay. And now we apply the result to the test set to get test error. Here test is the test data set is by removing your data set, removing this train IDs from the data set. So you have that, okay? And still scale the data, right? To scale the input variables, okay? Standardize it. The scale command just performs standardization, okay? And then you table this result. You can see there are 4 misidentified observations in the test set. Test set is 90. How many observations we have?
105.
105. Yeah, 105 observations in the test set, right? 4 out of 105 is not too bad, right? It's less than 4%. Okay. Test error. Of course, usually we are looking at a very complicated model. There are total 20 parameters with 19 weights plus one like the constant. Very complicated model. Now, suppose we use, and also we also look at the Hessian matrix. Here, the Hessian matrix is positive. As you can see, that all the eigenvalues are positive. Okay, there's no negative eigenvalues here. Right? You can see that on this printout. Okay, and suppose we apply different scaling method. Okay, remember in our class note we mentioned about this. We scale all the variables to be between 0.1 and 0.9, right? So here this I wrote very simple function to do this scaling. Okay. So here this capital S scale function. Okay, take a vector. Okay, and you scale the vector. The values of vector to be between 0.1 and 0.9. Okay. So simply this is function. From that, it's very easy to do. Okay. So here x and low is 0.1, high is 0.9. This is default. Well, I wrote this function in case you want to scale in a different ways here. But here we do this scaling. Okay, take any vector, we convert the values, the components of vector to be between 0.1 and 0.9. 0.1 corresponds to minimum, 0.9 corresponds to maximum. Scale is high minus low, so here this is basically the result. So here this is a scale function. Okay, so let me register this scale function, and then we apply the scaling separately on training set and test set. Okay. So let's say we have this. Let me run our result and expand this a little bit. Okay. So after this, the definition of the scale function. Suppose we start with this random seeds and then ID train. Let's just do the same thing here, a similar way. Okay. And this is a train ID. Okay. So just obtain the train set. And all you have to do to scale this, the columns of the input variables is by using the apply function. The apply function is really a very versatile function. Okay? You can apply to the columns. If you say 2 means that's columns. Okay? 1 means rows. Okay? In this case, columns. Columns are the measurements that we have. Okay? So apply to the columns of this data matrix. Okay? Well, actually, it's a data frame, but excluding the last column of species, all the rest are numeric. That's right here. Data matrix. Okay? With our scale function, this is a function we just defined. See, the flexibility of this function is that you can have a regular function like minimum, maximum, and so on. But you can also have your own function. Okay? So scale this return to the same structure as before, except that all the columns are scale. Okay? So you kind of wonder, you can look at that columns, all these columns are scaled to between 0.1 and 0.9. Okay? And then we do this neural network fit in again. And then we have a test set form, and then look at the test error. Okay. It's 2 out of 105. Well, this is too good to be true, isn't it? Okay. Really small error, but interpretation is really difficult. Okay, with this complicated model. Okay. But all the eigenvalues are positive, so it's positive definite. Okay. So actually, the optimum is reached in this case. Okay. Well, here, either way, the previous one or you do this way. Actually, these two are supposed to be identical. Okay? We use the same starting seeds and then here ID train. Instead of scaling train set and test set separately, we train the original data sets and then split that into train set. So basically, that's the same result. So here, doesn't matter if you run the previous way or this way. You're supposed to get the same result. Okay? Oh, no wonder, that's a test. There's something wrong here. Trace X ID train. So this is okay. Yeah, test set is not sorry. I forgot to change that to X because it's here. It's supposed to be X here. Otherwise you trouble. Let me rerun this. We don't need to run the Hessian metric that we already done. So here this is the result. Okay. Well, there's no place for us to interpret the result, okay, of this model. Okay. But here, neural network tends to over-interpret. Okay. You can see that when you apply some tests, it doesn't always give you the best result. Okay. I'd like to talk about our new topics today. This is about support vector machine. Okay, I don't know why they got this strange names for that. Support vector machines actually, this is actually, support vector machine is a generalization of generalized portrait algorithm. Okay? In the sense that this generalized portrait algorithm dealing with the sort of linear, in a sense, linear model. I'm not saying the linear model in the sense of statistical modeling, okay? And support vector machine is a generalization of that algorithm to a nonlinear case. Okay? So basically, that's what that sense is. Okay? It was first introduced in a conference. I don't know what that conference is. Anyone know about a conference name? I think this acronym is COLT, code conference. Anyone knows about this? I didn't Google it, but some kind of conference anyway. Maybe something about artificial intelligence or algorithm. It was first introduced, but of course this is gradually migrating from that generalized portrait algorithm to this. Okay? There are some intermediate results as well. Okay? These authors coined this term support vector machine in 1992. Okay? So see this term. Okay? Basically, this is inspired from statistical learning theory. Actually, this is a statistical learning theory developed by this author, Vebnik. Okay? First such book was in, I don't recall, maybe 1974 in Russian. Okay, anyone read that? Okay. Try it out. Okay. So this kind of algorithm is gradually evolving. Okay? And become popular because of its success in handwritten digit recognition. Okay. I think that's really important, right? So here you wanted to for a signature, you want to detect whether the signature is fraudulent or not, right? You can see that this is really an important result. Right? Because of their great success in the handwritten digit recognition, okay? And it's now regarded as an important example of kernel method. Okay? Actually, kernel method, this is moving from that linear to nonlinear. It relies on the kernels, okay? Some kind of kernel method there. Okay? And arguably, probably still true, right? I guess. Okay, still hardest area in machine learning. There are some like a variants of this machine support vector machine algorithm. Okay. Let's just look at the basic ideas of this support vector machines. Well, let's start with this the simplest case where data are separable. Okay, the two cases are completely separable because this is too good to be true, right? Okay. So here, this is linear machine. So basically, that's the original generalized portrait algorithm. Okay, because now it's you can translate, you can move this into nonlinear result. Okay? Where basically the two groups of observations, two classes can be completely separated by a straight line. Okay. So here, let's suppose you have straight line, because we learned about how we come up with a straight line separating these two groups. Okay. Well, of course, this is straight line formula for that. This is okay. It's W transpose X plus B, supposing that you have feature vector X, calculate W transpose X plus B. If it is positive, then you classify from class 1. If it is negative, classify from class 2. Okay, so different class. Just look at the signs of the result. Because with this complete separable result, any feature vector will result in either positive signs or negative signs, right? So you should be able to completely separate them. Okay. Plus signs assigned to this class, class 1. Next, negative sign is assigned to the other class. Okay. So basically, for convenience, you use yi to be plus 1 or minus 1 on this side, plus 1 on this side, minus 1. So very easy to see. Two classes. Of course, the problem is which is the best, right? Well, according to this, you can draw infinitely many lines there, right? Okay. But which line is the best? Okay. Basically, that is through the use of support vector machine. This is very lousy graphics. I didn't produce this carefully, but anyway, basically, it is produced through something called maximal margin separating hyperplane. Okay. Through this, the margin is 2 times c, right? Here, this is our separating hyperplane. Okay. And here, this is this line parallel to this hyperplane goes through the observation that is nearest this one. So here, this is C, and this is also C. This is shortest distance to these two observations in this group. Okay. And these three observations, okay, line on the margins, these are called support vectors. Okay. And usually, you can see that with this complete separable problems, there are only quite a few of these support vectors. Okay. In this case, there are only 3 such vectors. These are called support vectors. Okay. So idea is to try to maximize the margin equal to C in this case between classes. Okay. And that lines that halfway in between these two lines will be the separating point. Okay.
How do you pick those 2 points?
Yeah, that's the problem. Actually, it's through an algorithm. Yeah, it's through a quadratic programming. Yes. Okay. Yeah, through quadratic programming. Okay. Actually, we don't have to care about very detailed about this algorithm. Just say describe a little bit what happened. Okay.
Okay.
That's an important feature of this algorithm, actually, which is why it can be extended to nonlinear case, and it can be extended to when you have non-separable classes. Okay. So actually, it's through that the idea. Okay. But first of all, just look at this intuitively, right? Okay. Of course, the question is how we come up with that. Okay. Actually, this is optimization problem. Try to maximize C when you have here this length is 1. This is and then with this greater than or equal to C. Okay. This is this restriction a little bit stronger, but we can relax that restriction. Okay. To get rid of that constraint, we rephrase the optimization problem by this. Basically, is minimizing with respect to minimizing this function with respect to W and B subject to this constraint. Okay. It's actually this is a convex optimization problem. It's quadratic objective with linear inequality constraints. Okay. I guess for you are coming from industrial engineering, I think you're based on this kind of programming, isn't it? Okay. I think did you learn quadratic programming in any of your classes?
Not yet.
Not yet. Well, actually, let's say the algorithm is there. Let's computer take care of that. Okay, so here's support vector. Okay, will be defined by this. Okay, support vector will lie on this equation. Well, will satisfy this equation. Okay, where W equal this. Okay, this is mathematical form of that. and translate that into that here. This yi times this equal 1 basis on the support vectors here. And the classification rule is done by this. Okay. The reason is that our previous 2 slides. Okay. This is straight lines where that I have to go back and forth here, right? This W transpose xi plus b is positive, and in that case, y is also positive. So plus 1 times, or not just positive, it's 1, and so plus 1 times plus 1, you have 1 there. Okay. On the other hand, you look at this on this line. Okay, that W transpose x plus b is negative 1, and y in this side is negative 1. So product is positive 1. So actually, support vector are those feature vectors satisfying this condition. Okay. So basically, that's the idea. Okay. And the classification rule is done by this. And actually, you can see that the line depends only on a small number of training examples, as the one we have seen. There are only 3 support vectors. Okay. Okay. Let me go through this quickly. Some of these are of theoretical interest. So let's just see how we do this. Okay. Of course, there's important parts of this algorithm that later on, okay, then us to try to generalize this to the nonlinear case. Okay. Probably I should show this picture first. Okay. Probably much easier. So here, this is the separating plane, the green line, and here this is line where W transpose x plus b equal 1, and this is line where W transpose x plus b equal negative 1. On this side, we know that y is negative 1, right? Isn't it? So negative 1 times negative 1 is positive 1. Okay. So here, these 2 dashed lines are where the support vectors, okay, resided on. This is not exactly very good graphics, but supposing these are here, this is a support vector, support vector, support vector. There are 3 support vectors out there. Hyperplane realizing this maximum geometric margin, and from statistical learning theory, from all possible linear decision function. The one that maximizes the margin of training set will minimize the test, the generalization error or test error. That sounds good, isn't it? Okay. Because that's purpose. That's our purpose, right? Try to minimize the test error or the generalization error. And here, this is Euclidean distance. Well, this is just straight definition of distance between 2 points. Okay? From the decision boundary to any feature vector is given by this formula. Actually, only through this inner product. Well, this is sign. I think in this learning theory, they use this as the inner products of 2 vectors. Okay? You're not get used to this kind of notation. I think it's fine. Okay? Some prefer this notation for inner products. So here, this is the inner product of these 2 vectors. Okay? So here the distance is given by this. Okay? We can go through this quickly. So all we have to do with this parameterization, all we have to do is to search the space of WD to find the widest margin, right? That matches all the data points. Okay? The answer is on the quadratic programming. We don't have to know about the detail of this quadratic programming. Okay. As I on this, finding the decision boundary. Suppose we have a set of training points. Okay. Here, x1, y1 to x and y1 to be the training set, and yi is either +1 or -1. Okay. These 2 classes. Okay. And the decision boundary should classify all points correctly. Okay. If we have this result, right? Okay. You should have yi times this xi w base, that's w transpose xi, right? That's inner products anyway. Okay. Plus b greater than or equal to 1. Okay. So those support vector machines would have value equal to 1. Okay. This value equal to 1. Others would be greater than or equal to 1 for all I. Okay. And the decision boundary is determined by solving the following constraint optimization problem of this quadratic programming. Okay. Does it make sense or not? It's from that slide we said before. Where was it? Is this slide, right? So in this slide, we already talked about that. Okay. Here, this is boundary on this line. Here we have W transpose X plus B equal 1 and greater than 1 here. But anyway, all the class here are having yi equal plus 1, right? Okay. So positive 1 times greater than equal to 1 step greater than equal to 1. Okay. On this side, Wx plus B is less than equal to minus 1. Here, this is exactly equal to minus 1. But all the yi values are here negative 1, so making the result greater than equal to 1. So it's based on that. So we have this result here. So basically, if this constraint optimization try to minimize this subject to this condition, I guess you learn from calculus. So here you can use Lagrange multipliers. These Lagrangians of this optimization problem is supposed to be a space. Is finding this. With this result, where alpha I greater than equal to 0. I guess we all learn from calculus. This is how we, with the constraint optimization, right? Okay, we do this Lagrange multipliers for the result. Okay. Okay, so we get this result, and finally, you can see that example on dual variables, all the alpha i's will be 0 unless they lie on these two boundaries. So meaning that alpha i's is positive if and only if it's a support vector. So here we have, so here this is support vector because alpha I is positive. Okay? Here this is a support vector, alpha I is positive, and here another support vector, alpha I is positive as well. All the rest of the alpha i's are 0. And let's not worry about how they come up with this. I leave this for theoreticians anyway. Okay. So basically, resulting dual problem is to solve for alpha i's by using the quadratic programming solver on this objective function equation. Okay, where you have this alpha I, alpha j, yi, yj times inner product xi, xj. You can see that the objective function dependent through this feature vector only through the inner products. This is a very important feature. That's why later on, well, currently we talk about linear support vector machine, and this can be generalized to nonlinear case. It's through this observation here. So the problem depends on feature vector only to the inner products, nothing else. Okay. And also in addition to this, you can see the objective function does not involve b, right? The constant b doesn't involve that. Okay? So can be determined separately from the initial constraint. You don't have to use that. Okay, so this is basically a quadratic programming problem, and global maximization of alpha i's can always be found. Okay. Suppose that here, once you get this alpha star, actually that's a solution, right? You get alpha star and b star are found. Okay, you basically classify the new points x as sign of this. Okay, if positive, then you have +1 to class +1. Negative, you have -1 to class -1. Okay. Basically, it's just through the inner products. Okay. With this alpha i's and alpha star and beta star, okay, this is through the inner products of feature vector. So here this is a linear support vector machine. So the earlier this generalized portrait algorithm. Okay. You still argue that linear is possible, but how do you do that?
What if you have it not?
Well, this before we go into that. Okay. Here, this is an important finding. Okay? The solution of support vector machine is of the quadratic programming. It's only has a nice problem. Data enter in the optimization formed only through the inner product. Okay, the feature vector entering that through the inner product. Okay, nothing else. Okay. So non-linearization is possible. So basically, you probably see if you have a separable problems like this, okay, instead of the nonlinear case, it's possible to transform this. Suppose I have this. Okay. Try my best. Come up with this example, and then here you probably have something outside that. Okay. Say I have two classes case. Okay. So the support vector could be something of a nonlinear form, okay, rather than linear form here. Try my best to come up with. Probably another one. Okay. It's not really nice graph, but assume that we have, for this group, we have this 1, 2, 3. There's probably 3 points on the to be the support vector, the rest are not. Okay. Imagine there are probably small points here, okay? And for the outside group, okay, you probably have on the support vector, more likely to be just this one. Okay. So here there's another support vector here, right? There's a support vector. Of course, this is nonlinear case. This is not linear case. Okay. There's a support vector and support vector, support vector, support vector. And in that case, the separating hyperplane will be something in the middle here. Okay. I'm not really good at drawing this, but just imagine it, something like this. Okay. And the answer is right there, because original problems is for linear purpose, and then nonlinear is still possible. All you have to do is just do some kind of transformation. Okay? Transforming your data to a higher dimension. Okay? And that's the idea of the support vector. Okay? Make sense? Or not? Okay. It's only through the inner products of the vector. Okay? And you can see the characteristics of a solution. Many of alphas are 0, so making the problem not as complicated, simpler. Okay. And W is a linear combination of all small number of data points. Only few support vectors involved. Okay. And this is kind of sparse representation, can be viewed as data compressions as well, just like a k-nearest neighborhood, like something like that. Okay. And xi with non-zero alphas are called the support vectors, okay. Like the one we see in the linear case. And here these are support vector for this nonlinear case, 1, 2, 3, 4 points. Okay, there are 4 support vectors. Okay? And the decision boundary is determined only through the support vectors, nothing more, right? Isn't it? Like this example. Okay? The decision boundary only depends on these 3 points. Only depends on these 3 support vectors, not depending on the rest. Okay? So it's really, are we at this point? Oh. Yeah, right here. Okay. And actually, if these are the indices of the support vector, so we can write W as this, the representation of this support vectors only. Okay. And for testing with a new data Z, we simply just compute this result through this formula. Yeah. So it's ZW plus B, we just doing this. Okay. Result to get a result, and class Z as a class 1 if the sum is positive. Otherwise, you class as the other group. Okay. Now, of course, first, let's not jump into this nonlinear case yet, but this first, going to more relaxed situation where you have overlapping classes, not completely separable classes. That's what we do. Okay. Of course, the perfect separation is impossible because you have these non-separable problems. Okay, basically, simply just includes this arrow term instead of maximizing margin. Okay, you minimize this arrow plus lambda over margin. Okay, so it involves only a quadratic programming. So basically, this is a schematic class of this allows an arrow in that. Okay. So here, we do have a non-separable case, right? Then this one going over the other side of the hyperplane, and this is probably going within this separating margin, right? Okay. So basic idea is that allowing observation to add certain quantity. I'm not sure this. I couldn't recall from my learning from the programming course. I mean, not linear programming, not language programming. Okay. Is this called slack variable or not? You add in something there? I think probably it's called slack variable. It is? Okay. I couldn't recall the name for that, okay? It's called. Is it? Oh, I need to check that, okay? So, okay. So adding that quantities there to allow that, okay? So kind of assuming that basically, you kind of assume that this is a point from that side, right? But adding that will just go through it, okay? So if that is the case, then actually you are able to sort of separate in, and of course then you do see some error there, right? Some misclassified identities. So linearly non-separable problems allow some errors. XI in classification. So basically this is the case, okay? So we cannot find WMP that satisfies this exactly because we have this non-separable case, okay? Oh yeah, I put it there and I forgot. I have to check. So this is called slack variables. Okay, slack variables. So adding this quantities there, okay, allowing you that instead of having this greater than equal to 1, you allow this to be greater than equal to 1 minus this quantity. I never pronounced this Greek letter correctly. Is it Z or M1? No, epsilon. Huh? No, this is not epsilon. Epsilon is this. Well, no, this is not epsilon. this. I'm not really good at writing this, right? I don't know. Is it? Whatever that is. You add in that select variable, okay? Cause Z? Z. Since this is pronounced this, right? How do you pronounce it? Anyway. So if you make this, allow this large enough, you can always, the constraint can always be met. So anyway, leave this technical detail there, and then let's say we have finally have this result. So this is penalized objective function, okay? Instead of just original strict objective function, this is penalized objective function with this added terms, okay? Okay. And subject to this constraint. So this is like relax a little bit into this optimization problem. Okay. And minimizing this, you can this quantity can be obtained through this. Okay. These are slack variables in optimization. What is slack variable? Okay, actually, what's the meaning of slack? Is this the negative terms or positive term? So negative term, right?
Yeah.
Let's try to penalize, isn't it? Yeah.
It's surplus.
Or surplus. Okay, thank you. Well, anyway, so here this is how this non-separable case was sort of modified through the original separable case. Okay? So you just get ideas how this works, right? And then understand what is the meaning of support vectors. Okay? So optimization actually is just done through is actually through only quite a few feature vectors. Okay, so involve only quite a few feature vectors. So just make it computation feasible and easy. Okay. C is the trade-off parameter between error and margin. Okay. So actually trade-off into conflicting goals, minimizing the training error and maximizing the margin. Okay. Let's see how we going to balance between these two. Okay. And still non-separable problems, we still see this. Okay. The objective function still involve feature vector only through the inner product. Okay. So that's nice thing here. Okay. And the idea of the jumping from linear to nonlinear case is just do some kind of nonlinear transformation through the inner product. Okay. That's all we have to do. Okay. Or inner product of this nonlinear transformation. Okay. Actually, we'll see that later. Okay. So similar to a linear separable case, except that there is an upper bound C on alpha I now. Okay, so except for that, the rest are the same. Okay. And you can use a quadratic programming solver to find these quantities. Okay. This is good generalization in theory and in practice, and work well with a few training instances. That is only depends on few support vectors, right? You don't have to. It doesn't rely on the entire training instances. Okay? And you can find global based model, okay? Efficient algorithm because it's only done through few vectors, not all. Okay? And this is amenable to kernel trick, meaning that jumping from linear to nonlinear. That's why that's called the kernel trick. Okay? So here this is sort of through some nonlinear method. I guess I'm going to leave this. We're going to talk about this next time. So we start for the nonlinear case, the general case, like this. Okay. Well, in this case, this is completely separable case, right? Where you can actually find these nonlinear functions, sort of separating them. Okay. So here, this is separating hyperplane that a function that separates these two groups. Okay. Okay. Let me stop now, and we'll continue on this. Our section 3, this topic next time.